So in class today, we started talking about the idea of a tangent line approximation. Okay, so we're going to kind of continue that with this video. Go ahead and fast forward to wherever it is we left off in class. In every class, it was a little bit different. Okay, so the target for this lesson is that students will find the equation of a tangent line using the derivative process to approximate an unknown value. So when it comes to the tangent line, we know that at the point of tangency, that's where the curve and the tangent line actually intersect, so that point right there, that our function and our tangent line are exactly the same. But the tangent line has a couple purposes. One of the purposes that we use the tangent line for is what we call a tangent line approximation, sometimes a linear approximation, sometimes we call it linearization. So all those terms mean the same thing. And what we're going to do is we're going to use our actual equation of a tangent line. And I'm going to label that L of x. Okay, so our tangent line, we know that starts with some y value plus some slope times x minus the corresponding x value. We can use this tangent line to approximate the function at which it is tangent to, if we have that specific value. So at the point of tangency, that red point on the graph, we know that the function and the tangent line are in fact equal there. But for values around that point of tangency on that tangent line, we can use that tangent line to actually approximate values of the function. I can use that tangent line. Let me get a different color. So for instance, if I wanted to figure out what that point was on the function, I could use the tangent line to calculate it and get a really close value, a good approximation of it. However, if I was looking at maybe a different point, let's say this point right here, I wouldn't want to use the tangent line's point to approximate it there, because of the fact that there's too much distance between those 2 points. That would be a bad approximation. So the further we get away from that point of tangency, the worse the approximation is. But tangent line, finding the equation of a tangent line, I hope you guys realize is not really that difficult. We've been doing it for a long time now. If I have a different point, I can always create a new tangent line and actually use the new tangent line to approximate. So I can change my tangent line from point to point easily by plugging into the derivative, getting that slope. You kind of know that process. But this allows us to actually calculate values that are not really calculatable by hand. So for instance, if I wanted to calculate the third root of 8.1, well, I don't really know the third root of 8.1, but I do know the third root of 8. So if I calculated the third root of 8, I get 2. Like, that's a calculatable value. Okay, because 8 is close to 8.1, I can use that x value of 8 to calculate and estimate what it's going to be when that x value is 8.1 by choosing a value that I can calculate. So that's why I'm going to choose x is equal to 8. I'm going to use 8 to approximate the 8.1. And then I'm going to choose my function to using the same operations that I'm trying to do with the 8.1. I'm trying to do the third root of 8.1, so I'm going to use a function, the third root of x. And I'm going to create a tangent line using those two things. And that tangent line is going to help me to approximate the value that I can't calculate by hand. So let's start off by taking the idea of the tangent line. Okay. So the first thing we'd want to do, of course, is our first step, which is to plug in the value that we're going to be using, which we already did. Okay, and we got 2. The whole reason we chose 8 was because we can actually take the cubed root of 8. Second part of our tangent line process is to find the derivative. Now, that would consist of rewriting, so I'm going to do that really quickly. So if we rewrote it, put it in power form so we can use our power rule. This goes back to just that idea of the derivative. So 1/3 x to the negative 2/3. Then if I go ahead and rewrite that so that I can use it to calculate a value, it would wind up being like that. Then of course the third part of the tangent line process is in fact finding the slope at the x value that we chose. So 1 over the third, or 1/3, third root of 8 squared. Now 8 squared is 64. The cubed root of 64 gives us 4. And then once we multiply it by that 3, we get a 1/12. So our slope is 1/12 when our x is 8. The next thing we want to do is actually find the equation of the tangent line. Okay, so y equals, we start with our y value from step 1, plus 1 over 12 times x minus the x value that we chose. Now, I can easily plug in 8.1 into that equation. It's easier for me to calculate. It is something that I can actually calculate. So we're going to use the tangent line, that line right there, to actually calculate the value that we want. And what we're going to do is we're going to plug in the desired value, that 8.1, into the tangent line and just simply solve it. So I'm going to get a different color. Okay, so next thing I want to do is just plug into the tangent line. So 2 plus 1/12, and the x value that we truly want is 8.1 minus the value in our equation. And then it's really just calculating that by hand. That's easily done. So 2 plus 1/12, and then 8.1 minus 8 gives us 0.1. I'm going to put that in fraction form. So 1/10 there. And then really, I'm going to kind of work backwards. This gives us 1 over 120. And to add that to, we're going to need a common denominator. So 240 over 120. Let me go ahead and move that up. And then, of course, that means our y value is 241 over 120. And what that means is this third root of 8.1 is approximately 241 over 120. Now, if we put both those into the calculator, we'll see that those values are very close together. So that gives us a really good approximation. But if we think about it, 8.1 is probably about right there on the graph. If we think about those two functions are really not that far apart at this point in the function. So the approximation should be really good. In fact, I know that this is an over approximation. And I can tell that from the graph because my tangent line, that line right there, is actually above the function that we're using. Okay, so because it's above, therefore it's a over approximation. It's sitting over our function. Okay, so we can do this pretty much with any process. So for instance, if I want to use a linear approximation to approximate sine of 3, there's two things that I need to do. I need to first figure out the actual operation that's going on here. So the operation that's going on is sine. So I'm going to use a function that has that same operation on a random value, so sine of x. And then what I want to do is choose a value that's close to 3 that I can actually calculate with sine of. So when we talk about trig, we talk about trig in terms of radians, so pi's. So I want to choose a pi value that's close to 3. So I'm going to choose x equals pi, because pi is about 3.14, which is a value that's close to 3. So I'm going to use that to actually calculate what the sine of 3 is. Okay, so then all I do next is actually find the equation of the tangent line. So I'm going to start my process. So 1, we're going to plug in pi. So sine of pi, and the sine of pi happens to be 0. Okay. Step 2 is the derivative. So our f prime of x gives us cosine of x. Next step, sorry, that's a 3. It's a terrible 3. That's better, is to plug in. And the cosine of pi happens to be -1. And then the fourth thing I'm going to do is actually write the equation of the tangent line. So my y value is 0 minus 1, because our slope was -1, times x minus the pi value. And I'm going to actually plug in 3.14. Because remember, we're using this to approximate, so we want to approximate with values that we can calculate. So I'm going to estimate pi to be that 3.14 to help us out. And then the last thing I want to do is take that tangent line and actually plug into it. So if we take our tangent line and we plug in, I don't really need that 0 there. We're going to plug in the desired value. And that desired value is 3. And then all we're going to do is calculate what that is. So -1, 3 minus 3.14 gives us -0.14. And then when we multiply those, we get positive 0.14. So that means the sign of 3 is approximately 0.14. Okay, so something that we can't calculate, but we can approximate to a pretty good approximation. In fact, again, if you put both of those into your calculator, they'd be very, very close together. Okay, so we want to do these with things that we can't calculate by hand, but this is even more true when we're dealing with something that's not even a function, or not that we don't have an equation for. And that's kind of what that next page is. Okay, so if we go to our next page, we can do the same process with the table. So if we don't even know what a function is, but we have data from a function, we can use this tangent line approximation to, in fact, approximate values that we didn't even calculate or we didn't even draw points for. So it all starts with the idea of the derivative. Now, because I don't have a function, I can't get the exact value of f prime of 4, but I can estimate f prime of 4. Remember, when we talk about a derivative, remember this is just slope. So in fact, to estimate, I'm going to use my slope formula. Okay. So that means I need 2 points, because, let's not go there. Sorry about that. Remember my slope formula, y2 minus y1 over x2 minus x1. So if I don't have an equation to find the derivative of, I can estimate the derivative just using basic slope formula. And what I want to do is get a point. First of all, we're looking specifically at 4 here. So that's the point that we know, 4, 3. Now, if I want to estimate slope at that point, I can choose a point that's below it and above it and use my slope formula to calculate that. So remember, just remember in your table that the bottom here is your y value. So your y values are going to go on top. So if I take my y2, which happens to be 5, minus my y1, which happens to be -2, over, and now I'm looking at my x values, 5 minus 2, and then we just calculate it just like we would do with any other calculation. So if we do that, sorry, I'm making marks everywhere. 5 minus -2 gives us 7, and then 5 minus 2 gives us 3. I just want to double check to make sure that's correct. 5 minus -2 gives us 7, 5 minus 2 will give us 3. So that means that this is the approximation for f prime of 4. Okay, so we're using an approximation here because we don't have a function. If we had a function, we'd find it exact and it would be good to go. Okay. So now, if I do that, then I can write the equation of the tangent line because I'm looking specifically at this point. So I have an x and a y, and now I have a slope that's approximated at that point. So I can write the equation of the tangent line to be y equals, my y value happens to be 3, plus 7 over 3, and x minus 4. And now I'm going to use it to calculate values that are not even on this table, like, for instance, 4.3. If I take my tangent line, and let me give myself a little bit more room, I can actually plug in this 4.3 into my tangent line. And then all I have to do is calculate. So 3 plus 7 over 3. 4.3 minus 4 gives us 0.3. Again, we can use fractions, we can use decimals here. It's really up to us. Because 7 over 3 kind of is a weird fraction, I'm going to go fraction over decimal in this case. So 4.3 minus 4 is 0.3, so that is 3/10. And then, of course, adding it together, we're just going to do some calculations. So I get 7/10, which really means 3 plus 0.7, okay, which is 3.7. And what that means is f of 4.3 is approximately 3.7. And if we look at the table, going back to 4.3 would be right here in the middle of 4 and 5. So our function is increasing, so it makes sense that our y value is increasing there. So it's a little bit greater than that 3 that we see. Now we can tell whether this is an over approximation or under approximation just by simply graphing it. So I want to sketch a graph of this. Let's not do that. So I'm going to create a graph and I'm going to go back and forth. You guys can see it all on your paper, but I'm just going to create a graph really quickly. Okay. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Okay. I'm not sure how much I'll need. So just sketching out a graph really quickly. So then I'm going to use my points. I'm just zooming in a little bit. So let me get a different color. Okay, so my first point is, of course, 1, 0. So x is 1, y is 0. So there's one of my points. Then when x is 2, y is -2. So right there. When x is 4, y is 3. Okay. At 5, 5. Sorry, this is just a sketch. So it's not going to be perfect. And at 8, 6. So our graph kind of goes down, comes up, kind of curves. So our graph is going to look like that according to our table. Now if we look at 4, and we actually draw in our tangent line at 4, so that, remember, this was our point 4, and if we draw in our tangent line, we can see that the tangent line is on top. And because that tangent line is on top, I can say that this approximation is an over approximation. And I can say since right now the tangent line is above. Okay, so just that idea of using a tangent line to approximate a value that's not known or that's not calculatable. And this is especially helpful when we're dealing with a table. Okay, so go ahead and try the practice behind this, and if you have any questions, come see me on Monday morning.